Here we will learn how to use the commercial HLS tool targeting FPGA. We will use NEC CyberWorkBench to perform the three main HLS steps using the commercial HLS tools: resource allocation, resource scheduling, and binding. And we will learn how to verify the design work as expected, and learn how to use automatic test bench generator and create input file and perform RTL simulation. So creating a new workspace and give it a name, AVE8. Okay. And here we will set the project parameters. First, we need to set the target frequency here, and the FPGA device, and then the the standard library, which contains the information of the basic operation and functional unit, delay, and area. And those are device specific. If you are using another device, you will need to generate those library files. So here we will specify the frequency. So we will put the clock period here, and we will get the frequency. And here we are targeting the FPGA device. So from here we will use cyclone V. And here we will select the library file. So okay, apply. And after that, we will need to import the high level behavioral description file. In our case, it's a NCC file. And we will do parsing. First, we will do parsing, and parsing is check if there's any syntax error in the code, and the console window will indicate if there's any error. And after analyze, if there is like a green check, that means it's parsed okay. And we will get light blue folder with IFF file that will is generated if the parsing is successful. So this is the .iff file. That means the parsing is okay. After that, we'll need to do this synthesis setting. So from here, from this light blue folder, right click and go to synthesis option. And we will set the scheduling to automatic. That's the CWB will automatically time the C description at the scheduling phase. So, okay. And after that, we will need to create a functional unit constraint file. So here and concentrate, and we will set the upper bound for how many functional unit, large, middle, and small, uh, like a budget for this design. So we'll put those numbers and generate, and then from also from here we can do synthesize. So when we do synthesize, actually we are creating the RTL code, and we can see this is the .v. We can open it and we can see this is the RTL description, RTL architectural code. Other than that, we get QOR, which is quality of result, and this file will shows like it contains the all the synthesis information, the resource utilization, uh, critical path, latency, and other information. So to review the synthesis result, we can, like from here, we can check like the data path. And as we can see here, this is the data path circuit. And from here, we can check where is the critical path. Show that critical path is from this point to this point. And we can like do cross-reference with, like when we click on the circuit, we can see which cross reference with the C code. Also, we can see the signal table. This signal table shows the timing diagram of the synthesis when the input, like in our case, we have only one state. So when it's like enabling so when the input being read and the output register accessed here, this is the register and the output. This is the output written. And also what we can check the data flow graph, which is the result of the scheduling. So from here we can, from synthesis option, information, show data flow graph, and resynthesis. And this is the data flow graph. Uh, this is the scheduling result showing which operation assigned to which clock cycle. So the next step is like logic synthesis, which like converting the RTL code to get netlist, and from here we can do like logic synthesis script, and that's the will generate the t.tcl file, and then we can do logic synthesis. We have two options: a command user interface and uh, GUI interface. So we'll choose GUI interface, and that will allows us to launch the Quartus uh, within CWB console window. I'll pause the video. So as we can see, the Quartus Prime will launch within the CWB, and this is the RTL file, and this is the constraint file, and we can do logic synthesis here. I'll pause the video. And as we can see, everything looks good. And from here, we can do timing analyzer, and we can check the max frequency and the critical path and compare it with the number we get from the CWB. We can close it now. So the next step, we'll do design verification, and we have a software simulation, uh, and we have RTL simulation. We will start with the software simulation. And by the way, when we do the logic synthesis, we will get this red folder, which is the result for the logic synthesis. So to do the software simulation, we'll change to project tab, and here we have simulation work, and we will need to create a new simulation scenario, and we will call it AVE 8SW, and we will choose behavioral and C++. Okay, this is the source file, and here from the test bench build, we will add C to preprocessor definition. We will need to add the input. It's going to be text file, and then we can oh, sorry, I think I did it to the wrong position. No, sorry, it's correct. So now we can do build, and if we get this error, here, uh, if you get this error here, you can compile the code on the terminal window. So we need to go to the terminal, and we will need to go to the location where we create the simulation file. This is the location where we create this simulation file, and This code will create the .exe file. As we can see here, we have this, the .exe file, and this, the other command, and this command will compile the program. And as we can see here, we have the output data, and we can check it here. And this is represent the average output for the software simulation, for the code simulation. This is the output, and this is the input data. We did it through the terminal, and we can see here it's a green, and we can open the output data here, and this will be the golden file. Again, switch the simulation result through the different synthesis stage will be compared against. The next simulation, we're going to do the RTL simulation, which simulate the RTL generate the output match the golden output. So create a new simulation, and in this case, in this time, we'll choose RTL, and we AVE 8 8 RTL. Okay, and this is the top process, and here we're gonna choose model sim, and from test bench we're gonna choose the generating random data here, and here on the main right, input output data every cycle. And from the test bench we're gonna choose decimal, and generating random data here from data input data from pattern file, and from simulation we're gonna choose VCD and apply. Okay, and here we will need to upload, we will need to import the input, but within a different extension, should be to .clv file, input and output. And the reason we upload the output also because we will need to compare the output. This is the golden file. So here, build, and then simulate, and we will check that we have output file here with the same name as the output in the module. And when we open this, and we can compare it with this golden file, and we can see the results are the same. So other thing we can do here is we can with the HLS tools, it allows us to generate different architecture with different area versus performance constraints without having to modify the actual C code. This is mainly done by modifying the synthesis constraint like the FC&T constraint file on synthesis option. So go here and synthesis option. So here synthesis options, synthesis results. So we can see the synthesis window here. So here we can see this is different architecture with the same C code, and with these we can check, okay, how many lookup tables in different architecture and what is the latency. So in order to get like the history of what architecture will like what is the trade-off between any different architecture here, we can go change something here like the FC&T file. Here we can change those number and resynthesize the design and check the result. And we'll change this to 1 for each type. Apply, okay, and we will resynthesize. And if we go to the synthesis result, after changing those constraint here, before we resynthesize, we need to change this to manual. So the CWB does not generate a new FC&T file when resynthesize. So resynthesize. And now we can open the synthesize window, and we can see we have a new architecture with different lookup tables. So this is the new architecture. This is how many lookup tables. And this is the old one with this lookup tables number. And we can check the latency also. It's different. We can also check the critical path. This is the critical path and this is the critical path.